Hello everyone, I am Joyce Kane and I'm going to discuss about the rate of energy transfers by sinusoidal waves on a strings. So before we start, what is sinusoidal wave? So sabi dyan, a sinusoidal wave is a type of wave that has a periodic and smooth oscillation like a sine or cosine function. So a sinusoidal wave can be sent along string such as guitar string or a rope by creating a disturbance at one end. The wave will propagate along string with a certain speed, depending on the tension and the mass per unit length of the string. As the wave travels, it carries energy from one point to another. The rate of energy transferred by a sinusoidal wave on a string is the average power that the wave delivers to a point on the string as it passes by. The rate of energy transferred by a sinusoidal wave on a string depends on the amplitude and the frequency of the wave, as well as the properties of the string. The larger the amplitude and the frequency, the more energy the wave carries. The higher the tension and the lower the mass per unit length, the faster the wave travels and the more power it delivers. So, for example, the pulse lifts the black, increasing the gravitational potential energy of the black earth system. So, if we send a pulse down this string, we know that there's energy in it because it's able to lift this mass. The pulse lifts the black, increasing the gravitational potential. So, each element of the string is a simple harmonic oscillator and therefore has kinetic energy and potential energy associated with it. So, the kinetic energy is 1/2 mu squared. So, if we just look at a small portion of the mass, dm, dk is equal to 1/2 dm by squared. Remember that it's going up and down vy position. So, dk, what is the mass? The mass is the mass density times x dx, the small portion x, so dk is equal to 1/2 mu dx. And vy squared, so dk is equal to 1/2. Then we're substituting the vy squared. So 1/2 a times minus omega a cosine kx minus omega t squared dx, and that's equal to 1/2 mu omega squared. A squared cosine squared kx minus omega t dx. Now if we simplify to dk equals 1/2 mu omega squared a squared cosine squared kx dx, and that's what we're gonna use. So dk is equal to 1/2 mu omega squared a squared d cosine squared kx dx. Now, the integral, so k is equal to k of lambda, the kinetic energy of the wavelength, is equal to integral of dk, which is equal to integral of 0 to lambda of 1/2 mu omega squared a squared cosine squared kx dx equals. Now, the mu, the 1/2 mu omega square in a square, those are all constant. They came out of the integral, so it's 1/2 times mu omega squared a squared cosine of the integral of cosine squared x. Now, if you look in the integral of table cosine, squared the integral of cosine squared as dx is equal to x over 2 plus sine 2ax over 4a. Well, in this case, a is case of the cosine squared integral of cosine squared kx dx is equal to x over 2 plus sine 2 kx over 4k, and that's what we have in the third line. 1/2 mu omega squared a squared 1/2 x plus 1 over 4k sine 2kx evaluated from the lambda from 0 to lambda, and so you get 1/2 mu omega squared a squared times 1/2 lambda, and you're gonna end up with 1/4 mu omega squared a squared lambda, and so we copy this equation over here. K lambda is equal to 1/4 mu omega squared a squared lambda. Now the potential energy of lambda, if you go through a similar derivation, you'll end up with the same thing, 1/4 r mu up with the same thing 1/4 r mu omega squared a squared lambda. You'll see is the same as the k lambda, and so the total energy of the sum of those, will you have a 1/4 and 1/4, you end up with the 1/2 mu omega squared a squared lambda. So the power is equal to the transfer by mechanical wave divided by delta t, that's a lambda divided by by the period, so that's 1 half mu omega squared. A squared lambda over the period equals 1 half mu omega squared. A squared lambda divided by t. Well, what is lambda divided by t? That's equal to v. So the power is equal to 1 half mu omega squared. A squared kinds of velocity. That shows that the equation rate of energy transfer by sinusoidal wave on the string is proportional to the square of frequency, the square of the amplitude, and the wave speed. So the omega is the 2 pi f, so is the square of the frequency, the square of the amplitude, and the wave speed.